Welcome, everybody. My name is Michael Bussmann from the Center for Advanced Systems Understanding in Görlitz, and I'm very happy to be invited to this 24th HPC Connection workshop happening online, so I'm very happy all of you joined. Today I'm going to tell you a bit on how I think HPC systems will be used in the future as discovery machines rather than your standard HPC system running a simulation. And I'm going to tell you why I think it's important to go towards the mode of discovery at HPC systems. So today we are in an era of data-driven science. We have been always looking at data in science, so that's nothing new, but the volume, the rate, the quality and the complexity of data have grown to a point where it is very hard to look at the data for the standard scientist and to really grasp the complexity and amount of data by simple tools. And so the challenge here is neither really volume nor rate as long as the data is not complex, but since we're now getting complex data, for example, looking at the full Earth with high resolution and all the different mechanisms that for example, influence our weather, or looking at an organism from the single cell developed into a whole organism, or even on a molecular level, or looking at the fundamental constituents of our matter with X-rays or even with particle accelerators, looking at the very tiny parts that make up every matter at all. So in all these cases, we're looking at very highly complex data in really exascale volumes and at very, very high rates. So this is a big problem now. How do we actually deal with it, and how do we understand that? And so we are building all these wonderful, nice facilities that create that data, from particle accelerators to light sources to observatories to high-power laser systems and so on. And all these facilities are huge. They're expensive to use, and they really bring us very, very new insights into what is happening. So this is a wonderful time to live in, to have all these different new facilities coming up and delivering data that we have never seen before. But the challenge is now to make the most out of this data, to really enable us to see more with these facilities than we could ever do before. And this is sometimes where we really do big science. And so now the role of HPC, the role of data analytics at a scale, has become very, very important in science. And of course, this has been recognized. So here you see one of those headlines where people have really seen now we need to build dedicated systems to cope with that data. We have to go to new ways of using these systems and so on. So this is now the message that we're trying to convey and that we're trying to work on. But the science itself hasn't changed in its way that it's done. You still have the standard scientific workflow, but now it has really become HPC and data analytics driven. So now every part in that cycle is really dealing with much data, with much computation and so on. And so I think we have not yet embraced what this really means once we're going to really complex, high volume data. Let's do some data-driven science. Here's a facility called Oncoray, which does radiation tumor therapy. It's located in Dresden, next to where we are. And they're using particle beams instead of photon X-ray beams to do the tumor therapy, to really kill the tumor with radiation. So how does this work? In a standard system, you usually use X-rays to irradiate a tumor. Here's one in the head of a patient. You might recognize the nose on top of the picture here. And in the middle of the head, there is a big tumor outlined by a white line. And what you see here is that the dose, colored, so pink means high dose, blue means low dose, is really distributed not just where the tumor sits in the middle, but also where the rest of the head using X-rays. But if you use ion beams, particle beams, this means ions are the constituents of our atoms that are positive, that are sitting in the nuclei, that are basically the nucleus of our atoms, while the electrons are stripped away from the atoms. So it's basically what is left if you strip away the electrons of our atoms and keep the ions. This is the fundamentally positively charged nucleus of our atoms. And if you use those, the physics, the interaction with the tissue is actually different than with the X-ray beams, and you see that you can really focus the radiation to where it belongs, inside the tumor and where you want to kill the tumor rather than in the healthy tissue. So that's a wonderful technique. However, you need very big accelerators. Here's one of these machines in Heidelberg, the HIF. Great machine, wonderful technique, and it really is used for treating patients. You see a sketch down there. There's a patient in the lower right corner, and it's surrounded by 600 tons of steel rotating in order to really do the irradiation from many angles to really irradiate the tumor and harm the tissue as little as possible. But what if you could make this smaller? Here's a sketch, an idea of Umar Masood, one of my colleagues who has produced an idea of a laser-driven irradiation setup, where a laser comes from the left lower side here in that picture, creates a particle beam that is then transported by pulsed magnets to the patient. And all of this makes things much smaller. The accelerator itself is basically just a laser and a tiny foil, and the pulsed magnets make also the beam delivery much smaller. So everything becomes much smaller and thus could fit into more of a smaller hospital scale rather than these really large scales. So this is a wonderful vision, but we still have to understand how to go there. So we really have still to do a lot of fundamental experiments and understand things. So the idea is to take a laser, a high power pulsed laser, focus it on a metal foil to a very tiny spot, and by this drive the electrons inside the matter, the negatively charged electrons, away from the positive nuclei, the ions. And because we're doing that charge separation, we're creating a very strong electric field that then drives the ions to high energies and forms a particle beam of ions. So that's our idea, basically shooting with a laser on a foil. And in order to study this, you need to actually really understand on the fundamental level how to do this. So you really need to run HPC simulations. And so we did, and we had a wonderful experiment to look at, actually a levitating target. That's the easiest one you can do. There's nothing to hold that target. It's just levitating in free vacuum. It's a sphere. It's a wonderful tiny body. Everything is very nice. And our colleagues at Ludwig Maximilians University in Munich did this experiment quite some time ago, and it was a wonderful experiment. It really produced nice results. They just shot on the target with a laser and looked at the ion beam coming out. And we did not know exactly when they did the experiment what the results would be beforehand, because we already had access to a supercomputer for a limited time and needed to do the simulations before we actually got the experimental results. And one of the things was we did this at the Titan HPC system back then, and we had very limited time to do this, but we were able to actually do 3D simulations, real full-scale 3D simulations instead of 2D simulations. And here you see already the difference between our simulation and in 3D and in 2D, and the comparison to the final experimental results. So before we even knew what the experiment was doing, we just knew what would be the experimental parameters, but not the outcome. We then compared with the outcome, and we came pretty close. But you see, we really needed the 3D simulations instead of the 2D simulations. The comparison is not perfect because parameters vary a bit, and this is a very complex dynamic. But nevertheless, we got quite clear picture of what was actually happening and could reproduce quite well what we saw in experiment. But this really, at that time already, needed a lot of resources. 18,000 GPUs, 4 petabytes of high quality data in just 7 simulations, 60 million CPU hours. That was a lot back then in 2015. And Titan was the #1 system in the top 500 HPC list. And we have been redoing this thing, now going to much longer timescales, taking into account much more details on the laser itself, on the dynamics itself. Again, going for 100 million CPU hours on the Pittstain system, again using GPUs, but it's always counting CPU hours. And that was the #3 system in the top 500 back then. And we got the information that we should just reduce our data requirements and try to find a solution that is technically possible for CSCS, because the amount of data we produce could not fit on that system well enough, and for a long time. So we needed to do online analysis already. And this is still true. And why is this the case? Because these modern systems already produce data at an unprecedented scale due to the very fast calculation, but to the limited bandwidth. So you don't get that data out fast enough, and the I/O is really becoming a bottleneck by now. And even if you do compression, the problem is not that you're not reducing the data that you store finally, but that you're not really increasing the throughput, because the quality of the data is high, the complexity is high. So really it takes some time to compress it very strongly. It takes compute power. And so again, most time you now spend in computing, and the final throughput is not really reduced a lot. So you're really at the throughput throttle here. You have a throughput throttle due to limited I/O, and this is a problem. Okay, you could do experiments. Always as a physicist, you say if your theory doesn't help you, you have to do experiments. And of course we do. This is done at the European Exascale, at HIBEF, the Helmholtz International Beamline for Extreme Fields, where you use a huge instrument, the European Exascale, a free electron laser that is basically an X-ray laser that can make pictures on the atomic scale of matter. So that's exactly the scale we are resolving in our simulations. So we're looking at it at the same scale that our simulations are running now. And we're producing wonderful pictures. We're not producing real pictures in the sense of how you would look at that, I'm sorry. But we're producing scattering images that need to be basically interpreted in terms of what we really see here. But again, if we look at this in a fundamental level, then we see that even these instruments today go to petabytes of data in production and more. So we're really going towards petabyte per second sometimes at some of these instruments. So again, we're at the same scale now as the simulations, that we're producing a massive amount of high quality data at atomic scale resolution very often. And we need to understand this data, and this data can't be stored for a very long time, unfortunately. So what do we need, actually? We need, first of all, performant code, and this is, of course, you say, a very old thing to say. But in the last 10 years, nothing much has changed in this regard, because we have been seeing the advent of GPU computing and of many-core computing, but we're still at a very early time to really leverage this on a large scale so that everybody can use these machines and really make proper use of them. But now science relies on using these machines in a regular way to do a parallel analysis or a parallel simulation. So, and just an example, we have been running on Summit now, the #1 HPC system in the world, going with an IBM and NVIDIA architecture and basically using CUDA. And now the next upcoming system, one of those where we are already taking part, is Frontier, which will be an AMD-based system with OpenMP and offloading as the main programming model, and maybe HIP, which is much closer to what you would use when you're doing CUDA, but still you have to change your code again. And this is of course always true when you're going to the next generation of supercomputers, but this can't be done on a large scale. So you're still fighting with a zoo of different programming models, with a zoo of different architectures to really get your performance out of that. And this is why we said we don't want to do that. We don't want to have like 5 different codes running on different machines. We want everybody to use a single source with all those machines, and that's why we developed Alpaca, which basically gives you a general programming model that's very similar to CUDA or HIP or OpenCL, but that can be mapped to different programming models that are in existence by basically just doing the compilation and then going to the underlying programming model that you're using, like OpenMP and SYCL, and map the parallelism in your program to the hardware in an open way so that you can optimize for a certain hardware and really say that's where we put our threads on a CPU, that's where we put our threads on a GPU, and that's where we have common operations and synchronizations on these levels. So now you can use a single source, single programming C++, standard C++ model, and use all these different backends like CUDA or HIP or OpenMP or SYCL to compile for your hardware that you want to use. And you're always never ever losing any speed when looking into this. So here's a nice graph basically showing that the overhead in Alpaca, because it's just a header, mainly a header-only library that then compiles to a fundamental underlying high-performance programming model, is not that big. So that's a very nice thing. Of course, this changes when your code becomes more complex, but we've seen very similar results even with highly complex codes like the one you just saw that was doing the simulation of the laser ion acceleration, which is a full-blown particle in cell plasma code. So this is something very nice. Now you can have just one source and run on multiple hardware. But you also have to take care of the memory layout when you parallelize. It's not just parallelizing your execution, but also parallelizing really the data structures. And for this, we have low-level abstraction of memory access, the Llama library, which is now developed together with the people from Root, the analysis framework for particle physics, where you basically can have a standard data structure that you want to use in your code, that you define in your code, but we change the data layout according to the algorithm and according to the hardware used in order to optimize data access by it. So this is an ongoing project, and I'm very happy we're doing this. And this can be used together with Alpaca to really have optimum data execution, but also data layouts. And if you do this, of course, you can also go further and say memory allocation, memory copies, and so on have to be optimized. And we're doing this, for example, with malloc-mc, a small object allocator for many core libraries, where you can just do a simple new on 10,000 objects, and that's rather fast because you're really controlling the way memory is allocated on that device. But today, we're not so much compute bound anymore, except for, of course, if you're doing a lot of machine learning in your code. But in complex simulation codes and even in complex analysis codes, data flow becomes much more important. You really have to take care of how the data flows in order to really make optimum use of the compute machinery you're on. And this might be standard to actually look at a task system also next to data parallelism, but the problem is to really describe data dependencies in modern code is still a bit tedious. This has been done very well now in large-scale data analysis, but not so much in large-scale simulation code. So we developed wrapped grapes, where you basically just have a very, very nice way of describing data dependencies. And if you describe the data dependencies in your code, so saying which part of the code needs different inputs from other parts of the code, this goes into a very complex pattern of communication going from a single GPU or CPU and different parts of the memory to full MPI communication and even the file system. And once you describe just the dependencies, this can then result in a task graph and creating this very complex communication patterns that you can then in the follow-up optimize for optimizing your code. So very few code and very actually intelligent code, because you're describing the data dependencies and not the real communication, leads to very complex communication patterns that you can then create automatically. Another thing is I/O. As I said, storing stuff has really become a big problem because you don't want to look at it offline anymore. You need to do much more online while the simulation is running. And so here's a little thing we teamed up with the 8 years people from Oak Ridge National Lab, even back then when we did the Titan calculations, and we already saw a 20-fold increase to using standard I/O libraries that are very widespread and very, very successful. But once you really look at I/O, you see this hierarchy in throughput from, for example, a GPU down to a parallel file system. This is many, many orders of magnitude. And so what you really want to do is basically stream what you have in your analysis framework or in your visual analytics framework, because you don't want to store everything, but just make a selection of what you want to store. And that you can do with either very intelligent algorithms or by interacting with the user and really having the user take full control of what is happening. And first, what you do is, if you look at a complex system, and in our case, this is more and more often the case, even a simple single simulation that already is very complex by itself now needs to be coupled to even more complex simulation that produce the signal you're looking at in experiments. So now what we do is we couple really the output of one simulation to the next simulation and do this in memory and really produce not I/O to disk, but I/O to the next simulation and the next simulation, creating a full virtual twin of our experiments that we do at the European XFEL at the same scale with exactly the same parameters as we are seeing in experiment, and finally to really the level of replicating everything in the experiment we can. And this involves a lot of different simulations running at the same time, talking to each other, exchanging the different output via the memory of the system. And now we want to control this. Now we really want to go in there, take the experimental data that we took or that we are actually taking at real time, fuse this with the simulation data and put the scientist in the center of this process and making the scientist available to interact with that data intelligently. So the first thing is, of course, you think of simulation and visual analytics, visualization. But if you really look closely at how science is done, science is driven by quantitative analysis. And many people think of using Python for this and are doing this with Python. And Python is a great tool by itself, is a great language by itself, and just also because it can be used interactively, just in time. But for many systems that we're talking about, to really get to the really high throughput, you need to do some more core level languages like C++. And here's one of these examples that we've been working on together with the CERN people to really use a just-in-time C++ compiler and add CUDA to it, and add to it the Alpaca possibility of really running on different hardware, on accelerator hardware, even on FPGAs in real time, just-in-time compilation, and now putting that in a Jupyter notebook with the help of the XUS and Xtensor libraries. And now you can have 100,000 lines of code and just-in-time change a few of them and really do your analysis in your Jupyter notebook as you would do with the Python code, but now really with C++. But then again, you also want to have visual feedback. So you're doing the quantitative analysis, but you also want to do really the explorative analysis. So you really need to have these terabytes of second and even more produced at these machines, both at the experiments and the simulations, to be visualized. And then you realize that you really need to do close strong coupling between the analysis, the HPC software, and the visualization. And that's what we did in Isaac, where we do not copy data anymore. We just reinterpreted data that's produced either in experiment or by simulation directly on the fly and use this as an input. And when we do this, we really get to terabyte per second visualization capabilities live. So here you see that we can actually run on a large-scale HPC system that's producing 10 to the 10, 10 to the 11 particles at the same time, and then do a full rendering live and really interact with it. So this is how we now run on Summit. We use the full system. We go in, we can have direct interaction with the system, look at it, look at different data sources, put different markers there that tell us something on energy or direction or whatever. And now what you see here is, because we really can deal with that much information at the same time and give direct feedback visually, we can of course use this information as an input to semi-automatic or even automatic analysis routines. And here in comes now the role of machine learning, where we basically couple the output of our simulations and experiments to large-scale scalable machine algorithms and interpret this data together with a scientist that gives feedback both to the machine learning algorithm in a supervised way, but also then during the interaction more in an unsupervised way, until we really find what data is interesting, what needs to be stored for long-time exploration, long-time understanding, and what can be thrown away and what is not interesting. And this is just the very first step to do HPC as an exploration tool, and really do exploration with this. We now need to put in more hypotheses. We now need to change the simulation code more interactively. We really have to put more knowledge into what is happening. So the tools I've presented today are just a very few tiny steps to what we are doing. We are now really in the time where the single scientist needs to interact both with large-scale data from simulation and large-scale data from experiment coming out in a streaming manner in a single place, and they need to be able to interact with that data, understand that data, and get very much help from intelligent machine learning, AI-driven algorithms to help them select what data is important, how it should be represented, and what is really important in the system they're looking at. And I think we're just getting a glimpse of where this is going for the future. And we're here at the Center for Advanced Systems Understanding trying to build some of those building blocks that in the future might become more important to deal with these systems on all scales. So I'm very happy again that today I got the opportunity to talk to you, and I hope you are looking at some of our projects. All of these are open source, so don't hesitate to actually have a look at them, try them out, and so on. And with that, I thank the organizers again for having me and wish you a wonderful time from the Center for Advanced Systems Understanding in Görlitz in Germany. Thank you very much for your attention, and bye-bye.